Leetcode 190 reversed bits. It's an easy problem, but only if you are well versed in bitwise operations. And for most of us, we operate mostly in the realm of higher level languages and higher level concepts. And even though those are the most fundamental concepts in computer science, in programming, and so on, we don't really use them that often for most of us. Yeah, of course, if someone works in embedded systems and with hardware, then they probably use it a lot. But for most of the developers nowadays, it's not the case. And that's why it might be a bit tricky and not that easy. So we will try to understand everything related to this problem and all the bitwise operations that are necessary in order to solve it, and how to use them and why should we use them. And that's it. So now let's start reading the description, which is very short. Reverse bits of a given 32 bits unsigned integer. Yeah, so reverse is the keyword. And basically what they mean with this reversion is not flipping each bit like from 0 to 1 and from 1 to 0, but flipping it in another dimension. Yeah, so if you read your number in the binary representation from left to right, yeah, then after the reversion you would get it as if you were reading it originally from right to left. And that's what they mean by it. And the 32-bit is important as well, because there is an upper limit on how many on how big of a number can you store using this binary representation. Of course, this limit is necessary because of the hardware limitations. In theory, we can think of like when we are thinking about them in mathematical way, they can have no limitation, but in practice they have, of course. So 32-bit can only you can only use 32 digits for such number, and each digit is of course that bit, which can be either 0 or 1. And so if you fill them all with ones, yeah, and convert it to a decimal, that would be your biggest number that you can store on such a system. And of course, you can have theoretically any number of bits. There could be a number which have just 8 bits, and that would be that would allow very limited number of numbers to be stored, but there could be many more as well. Yeah, so 64 bits, I think, is more common, or even 128 in some languages. You have like those long types, but in Python, for us, we don't really care usually about the types, because it's handled behind the scenes by the language itself. And here we have this on the right side, that hint of an int. Yeah, but this is only hint, and we cannot really control the details like in other languages, like let's say C or C++. And here are some notes related to Java. And there is no unsigned integer type. In this case, both input and output will be given as a signed integer type. And so there will be a different input cases for different languages. That's what they mean. And they should not affect your implementation, as the integer's internal binary representation is the same, whether it is signed or unsigned. Yeah, so basically you should not worry about the language you are using. In Java, the compiler represents the signed integer using 2's complement notation, and here is the link to a Wikipedia article if you want to read it in detail, but it's not really necessary for us to right now discuss it in order to solve this problem. That's why I would prefer to skip it. And therefore, in example 2 below, the input represents the signed integer -3, and the output represents the signed integer minus some big number. Yeah, I will not attempt to read it. And from examples, the only thing that you should really care about is this understanding what this reversion means. And the first input is this big number, output is even bigger number. But if you take a look at the explanation, you have the binary representation here and here. And just take a look at the last two digits are both zeros, and here the first two digits are also both zeros, then the next three are ones. Here the next three are ones, and the next two are zeros, the next two are zeros, and so on. So this is the only thing that you can really get from this explanation and those examples is what they mean by this reversion. Yeah, and now of course we have to think about what kind of bitwise operations there are in general and what can we use specifically for this problem. So let me copy that and we'll think about it in detail. This as well. Yeah, like this. Do back this. Can make it a little bit bigger so it's better, more visible. Reverse bits. Yeah, and we'll go back to that example in a second. But basically, the bitwise operations that we should know are the following, and I will explain shortly what can we achieve using them, what do they represent. And the first are shifts, either left or right. And other two are bitwise OR and bitwise AND. And if you know how they work, you can construct an algorithm using those three or those four. In fact, because there will be shift to the left and shift to the right. You can construct an algorithm using those that will rely on those operations, and that's how you can solve that problem. So let me explain what I mean. Algorithm, singular. The first step will be to initialize a helper variable. A helper variable, we can call it result. Yeah, and of course we initialize it to 0 or create a helper variable, and here we will store our result. Yeah, that's why I call it result. And I can add a small note that 32-bit integer, of course, at the beginning all zeros. Yes, so you will have like 32 zeros. As you can see here, we have 32 digits. So this one at the beginning will have all of them set to 0. And then we enter a loop with how many steps? 32. So create a loop with 32 iterations. And then each iteration has the following steps or sub-steps. If we call them steps, then here is like the body of the loop. And inside we'll shift. That's the first bitwise operation we'll do. Shift the result by 1 to the left. Yeah, and this can, of course, be done at the beginning or at the end. But it's easier to do it at the beginning since I think that, or at least I cannot think of a way to do it at the end without additional if. Yeah, so if you do it at the beginning, you have all zeros. So like the first time you do it, it's more or less useless. But then for the other 31 steps, it will be shifting the modified number. Yeah? So what do we mean by shift to the left? Let's create like a fake digit called A. Yeah, and basically shift to the left will shift everything to the left by 1. Yeah, and like this. Yeah, so what was here, the 0 will go here, the 0 will go here, by 1. Of course, you can shift by any number. But the interesting part happens at the border, since we said that 32 bits means that we cannot have more than 32 digits. So what does this last or the first digit, however we want to look at it, what happens to it? It will disappear. So here from this side, from the right side, a new 0 will pop in, and the last digit from the left will disappear, and all the others will be shifted, in this case by 1, but of course shifts can be by any number. And after that, we want to, why do we shift it by 1? Because we want to add extracted digit, or extract the last digit from n. Let's use this naming as they called. So this is our input variable, and add it to the result. Maybe not add, but append. So that's why we are shifting. We will create a new space at the very end, and we add a new 0, and then immediately after that we will extract the last digit from n, from the input, and replace the 0 with 1 if it's 1, and if not, then we'll leave it as 0. So either way we can call it append. It's not a really append, but that's what we want to do. And then, since we used the last digit, we can now remove it by shifting the n by 1 to the right. So as we said, shifting to the left moves everything to the left, and the first digit gets removed, and the new 0 pops up from the right, and shifting to the right is the same, but in the other direction. So here comes new 0, and by the end you will lose the last digit. And that's it. That's the whole loop, and it's all constant. So it's it doesn't depend on the size of n, so it's like all one space, both space and time complexity. And the thing is, how do we do this extraction? So you can extract the last digit by using bitwise AND, and you can append by using bitwise OR. Because no matter what you have, either you will have 0 or 1, you have only two options, and we always shift, meaning that there always be here at the end 0. So if you have 1, the bitwise OR will result in 1, and you will get 1. And if you have 0, then here is also 0, and 0 or 0 is still 0. So you will end up with the same number either way using bitwise OR. And bitwise AND will allow you to get the last digit, because if the last digit is 1, then you can do 1 and 1. This will result in 1. And if the last digit is 0, then 0 and 1 will give you 0. So that's why that's how can you extract the last digit, by using the bitwise AND. And that's it. Let's now maybe play with it. We will not do probably the whole thing. Let me copy that. Sorry. Let me copy that here. Control C and Control V. Okay, this time it worked. And that's our input. That's our N. So let me make it here. N is equal to, and the result at the beginning is equal also to 32 bits, but all set to 0. So let me replace those ones with zeros. 0, 0, 0, 0. And in the first, let's copy this. In the first iteration, we will just shift by 1. extract the last digit is 0, and append it here. So at the end, in the first iteration, it will look the same. Same thing will happen. So let's maybe out here some steps showing that we are iterating. Same thing will happen in the second iteration, because we again extract the last digit. The last digit will be 0 in this case, and again the result will look like this. But maybe we can show that the n will change. So let's try to modify both. None. After the sheet. So we'll modify both n and the result. And in the second step, of course, also n changes. Bam. That's it. And we get 0 from this side. And now we have reached finally the third iteration step. And here finally the last digit is 1, and this one will get appended here. And we will of course remove it. So after the third step, that will be the state of our variables, and then we can continue with all 32 steps. I will not won't be able to present them all here, but I hope that you get it now. And first we would shift to the left, and finally we have something different in the result than just zeros, and then we'll extract again the last number, and the last number here will get appended, and that will be the state after the fourth iteration. And of course here we will remove the last digit and shift by shifting to the right. Okay. And we could of course continue with all the 32 steps, but that would take too much time. I guess that by this time you should feel on what I was trying to explain and have a very deep understanding of the whole algorithm, so we can proceed to implementation. So let's create the result. Let's return the result. And let's do our iteration for underscore in range 32. We will shift the result by 1 to the left, and then we want to extract the last digit. We can extract it like this, and we can add it, append it to the result, to change the last digit of the result if here we get 1, and then we can shift n to the right. And let's see if that works. And wrong answer. Let me check. And return 0. Sorry. We should return the result. Now everything works in the first two cases. So let's see all the cases. And we beat around 50%. But if we try resubmitting, sorry, we bit according to memory. I didn't notice, haven't noticed how good was our first attempt for the runtime, but right now it beats 94%. And there is one bit more complicated, but even faster approach. But we won't do it now. Maybe I will do it in some other video.